Okay, in this video, we're going to balance redox reactions, and we do that by using the half reactions method. So let's start by introducing what a half reaction is. A chemical reaction that involves oxidation and reduction can be broken into two separate half reactions. Okay, one where the oxidation is happening, like here, tin is losing electrons going from 2 plus to 4 plus. That's the oxidation half reaction. The reduction half reaction is iron gaining electrons going from 3 plus to 2 plus. Okay, and adding these two things back together will complete the overall reaction and the electrons will get canceled out. Okay, and we'll just add these two reactions back together to get the overall reaction. Okay, and it's this method of taking a reaction, breaking it into two half reactions, balancing them, and then adding them back together. That is the method of half reactions that we're going to use to balance redox reactions. Okay, but first just wanted to show two separate half reactions. Now, let's use this half reaction method to balance redox reactions. Remember, in the previous video, we introduced this concept of reduction, gain of electrons, and oxidation is loss of electrons. And we called a chemical reaction where those two things are happening a reduction oxidation or redox reaction. But now we need to know how to balance redox reactions, and it's a bit more difficult than just regular chemical reactions. We use this half reactions method. Okay, and I know this looks like a lot of steps, but the first three are really the balancing part. The rest after that is sort of just mathematics. So let's concentrate on these first three steps. First, we're going to take a chemical reaction and break it into two half reactions and balance them separately. And when we balance these half reactions, we're going to start by balancing what I'll call the others, right? Not oxygen or hydrogen, but there'll be other elements involved, maybe carbon, maybe iron, maybe tin, like we saw in the previous one. We're going to balance those elements first, and then we're going to balance oxygen, and then we're going to balance hydrogen, and then after that, we're going to balance the electrons. So first start by balancing the others, and then balance the oxygen, and then balance the hydrogen, and then balance the others. So just writing out others sort of helps me remember that balance the others first, and then others has O first, and then H, and then E. Okay, so that is the order that we are balancing the elements and then the electrons in this half reaction. One other thing I'll note is that we are not balancing oxygens or hydrogens simply by changing a coefficient in front of oxygen. We are balancing them by adding actually, let me use a better example here. Adding oxygen in the form of water. So for example, if our half reaction looked like this, and clearly we were missing two oxygens on the left, we can't add those oxygens as just O2. We add them in the form of water, where each water has an oxygen. So we need two waters on the left. That's what I mean here by balance oxygen using H2O. And likewise, if we're now missing hydrogens on the right, there's 4 hydrogens on the left here. We need hydrogens now on the right to balance this reaction and make sure all the elements on the left and right are the same. We need hydrogens on the right, so we have to add this in the form of H+. That's how we're adding hydrogens, and we need 4 of them to balance the 4 we've introduced here in water when we were balancing the oxygen. Okay, so let's put this into practice. Concentrate first on breaking the overall reaction into two half reactions, balancing the other elements, then oxygens, then hydrogens, then electrons, like we'll see in a second. And then we'll worry about smashing those two half reactions back together and make sure everything works out. So let's look at this example where we're going to employ these 7 steps. Let's consider the reaction here between MnO4- and C2O4 2-, making Mn2 plus and CO2. As extra practice here, we can go through and just assign oxidation numbers, -2 for oxygen, so -8 overall. So manganese has to be +7 for the -8 and +7 to add up to -1, the charge on the overall molecule. oxygen -2, 8. Carbon here has to be +3 for them to be 6 plus total, so that when added to the oxygen's total, we get -2 overall, the charge on this species. Manganese on the right is going to be 2 plus, and oxygen -2, and carbon +4. Right, so carbon is going from +3 to +4. It is being oxidized. Manganese is going from +7 to Mn2 plus. It is being reduced. So now we're going to break this reaction into two half reactions. One is going to be the reduction half reaction. So it's going to incorporate manganese species on each side. And the other reaction is going to be the oxidation reaction. So it's going to incorporate the carbon species. Okay, so this is step one here. I have made two half reactions, one for oxidation and one for reduction. And I'm going to now balance these separately. So let's just choose one. Let's choose this oxidation reaction first, go through and balance that one. So here it is. And we start by balancing the other elements besides oxygen and hydrogen. So here that's carbon. We have a carbon element. We need to balance that. There's 2 carbons on the left, so we need to squeeze a 2 in here on the right, and that's what I'm now showing here. Okay, and so now there's going to be 2 carbons each side, and all these other elements are done being balanced. Now I can proceed with balancing oxygen and hydrogen. There are 4 oxygens on the left, and there are, well, 2 times 2, 4 oxygens on the right. So that is already balanced. So that's good. And now I can balance the hydrogen. Well, there is no hydrogen on each side, so that's already balanced. That's great. So now I've balanced the others, carbon. I've balanced the oxygen, and there are no hydrogens, so that's effectively balanced. And now I can move on to balancing the electrons. And this can give students some confusion here, and it's easy to make a mistake and add electrons to the wrong place. What I suggest is go through all the species on the left and add up all the charges. So there's only 1 species here. It is 2 minus. So overall, there is 2 minus on the left. There are 2 carbon dioxides on the right, but these are neutral overall. So there's no charges on the right. And so now I need to balance this charge. 2 negative on the left, 0 on the right. And I can only balance the charge here by adding electrons to one of the sides. But electrons are negative. So we always compare these two numbers, pick the larger of these two, and add electrons to that side to bring that number down to match the lower number. Right? So here I'm going to choose the side that is 0, and I need to add 2 negatives to that side to make the charge now 2 minus total on the right, so that it matches this lower number that is on the left. Okay, so that's what I'm showing down here. I've added 2 electrons. Each electron is -1, so 2 electrons here make this 2 minus overall on the right to match the 2 minus overall on the left. Great, so now my carbons, oxygens, hydrogens, and now electrons are balanced. And at this point, I have to go through and balance the other half reaction. So let's look at that one here. Let's start by balancing manganese, and then I'll balance oxygen, and then hydrogens, and then electrons. Manganese, 1 on the left, 1 on the right. Great, balance. Oxygens, 4 on the left, none on the right. So I need to add oxygens, but remember, I'm not adding them as just an oxygen atom or diatomics. No, I have to add this in the form of H2O. And so if I'm adding waters to the right, in order to add oxygens to the right, I'm going to need 4 waters on the right to balance the 4 oxygens I have on the left. Okay, so that's what I'm showing down here, and now my oxygens and manganese are both balanced. Now I can move on to hydrogens, and I've introduced hydrogens here when I was adding the oxygens in the form of water. So now I have 8 hydrogens on the right and none on the left. So I'm going to need to come in here and add hydrogens to the left side, and I'm going to need 8 of them, and I'm adding them in the form of H+. I'm not adding just 8H. I'm not adding H2s. I'm not adding waters to get my hydrogens to balance. To balance the hydrogens, I'm using H+. And I'm going to need 8 H's on the left. Okay, so that's what I'm showing here. So now my oxygens, hydrogens, and my manganese here is all balanced. 1 manganese, 4 oxygens, 8 hydrogens, good. And now I can balance the electrons. So let's go through and add up all the charges on the left. I have 8 pluses. H plus, there's 8 of them, so that's 8 positive charges. There's a single MnO4 1 minus here, so there is a single -1. 8 positives and 1 negatives, that's 7 plus overall, right? Positive 8 minus 1 is 7. And on the right, I have 2 plus and 4 waters, but those are all neutral. So overall, I am 2 plus on the right. Which one of these numbers is bigger? Well, 7 plus. So I'm going to need to add electrons to this side of the reaction where the bigger total charge is, because electrons are negative. How many do I need to add? Well, 7 to 6 to 5 to 4 to 3 to 2, that's 5, a difference of 5. So I need to add 5 electrons. 7 minus 2 is 5. And that will get my charges to be equal. Okay, so that's what I've shown here. 5 electrons on the left, and now my total charges will balance. 5 negatives plus 8 positives plus 1 more negative is 2 plus overall on the left and 2 plus overall on the right. Okay, so all of that just to do the first 3 steps here, balancing my 2 half reactions separately. Now I want to add these 2 half reactions together, but before I do, I need to make sure that the electrons are going to exactly cancel. And so I'm going to write my 2 balanced half reactions side by side. Here's the first one we did, and here's the second one. And before I add these together, I need to make sure that the electrons are going to perfectly cancel. They won't here because 1 is 2 and 1 is 5. So I need to multiply one of these reactions, or maybe both of them, to make these equal. So just figure out the common multiple here. 5 and 2 is 10. So I need to do something to these reactions to both make them have 10 electrons. Well, let's multiply the first reaction by 5 all the way through, and multiply the second reaction by 2 all the way through to get 10 electrons and 16 hydrogens and 2 MnO4s and 2 Mn2 pluses and 8 hydrogens and 5 C2O4s and 10 CO2s and 10 electrons, or to look like this. Okay, so now this is the result after I've multiplied through to get the common multiples of 10 for my electrons. And now when I add these 2 together, those electrons will cancel out. And that's what I want. And now what's left here is the balanced redox reaction. Okay, I'll clean that up and just show it here. So this is my final answer. All of that just to answer a single question of balance this reaction. Okay, so that is how a problem would look. It would just give you this chemical reaction and say balance it. You need to break it into 2 half reactions, go through all that rigmarole, find out a common multiple for the electrons, add it all together, cancel the electrons out, and simplify to here. Okay, now if you could go through and divide all of these coefficients by a number like 2, you would want to do so. But here you won't do that because this 5 would turn into 2.5, and we don't like decimals like that. We want integers. So we can't go through and divide everything by a number. That's okay. And so we're more or less done there. Okay, so we added the half reactions back together. We don't need to divide by a common factor because there is none. But let's now double check atoms and charges to balance. Okay, there's this other small thing here I'm ignoring for the time being. I'll discuss in a second, but let's just double check and do this last step here that all of our atoms and charges balance. Okay, so let's just look at all of the elements. 16 H's on the left, 8 times 2 is 16 H's on the right. 2 manganese on the left, 2 manganese on the right. 5 times 2 is 10 carbons on the left, 10 carbons on the right. Oxygen, well, 2 times 4 is 8. 5 times 4 is 20. So there's 28 oxygens on the left. 8 times 1 is 8, plus 10 times 2 is 20. There's 28 oxygens on the right. So all the elements are balanced. And now let's just make sure the charges are balanced. 16 pluses, 2 minus, and 5 times 2 minus 4, 10 minuses. So 16 pluses minus 2 minus 10 means overall on the left side I have 4 pluses. And overall on the right side I have 2 times 2 plus. And the other things are all neutral, so that's 4 plus overall. So yes, I have verified everything is great. So that is my balanced redox reaction using this method of 2 half reactions. Now, this is everything we have to do when it says balance the following redox reaction. And it would say balance it in acidic conditions. Or it might just not tell you the conditions, at which point we're just going to assume acidic conditions and stop here. And acidic conditions, because we have H pluses, right, floating around, that is an acid. Okay, so if the problem doesn't specify or just says acidic conditions, we will do everything that we've done here. If, however, the problem specified instead, balance the following reaction in basic conditions, well, there's an extra twist at the end. And that is that we can't leave H pluses floating around. We need to have OH minuses, or a base, floating around. So we will make one change at the end. Let me just clean this up so I can show you what this would look like. And the way we do this is everything is the same until we get to the very end like this. We're going to turn these H pluses into OH minuses. How do we do that? Well, to cancel out H pluses, we need to add 16 OH minuses. And whatever we do to the left, we will do to the right. Okay? So if it's basic conditions, balance it all the same, and then at the end, find the H pluses and add that number of OH minuses to each side. The OH minuses will cancel, or I should say neutralize the H pluses to make water. So you are turning those H pluses effectively into waters through the addition of OH minus. Just make sure you're keeping track and adding those 16 OH minuses to the other side. And then you have to figure out if waters can now cancel on each side. So we've added 16 OH minuses to neutralize those H pluses, adding 16 OHs to both sides. And doing so on the left, we've created 16 waters, which now the 8 waters on the right can cancel some of those waters. And so my left side will be 8 waters instead. And so now, in basic conditions, this balanced redox reaction will look like the following. Okay, now there's OH minuses floating around, not H pluses. So it's basic conditions. We can still and should probably go through, and especially for hydrogens and oxygens here, make sure those are balanced. 16 hydrogens on the left, 16 hydrogens on the right. 8 plus 8 is 16 plus 20 is 36 oxygens on the left, and 20 plus 16, 36 oxygens on the right. All right, so we've done that correctly. So if it says basic conditions, you need this one extra step at the end. Okay, so you can see these are long and difficult, and it's a lot to keep track of. So make sure you're practicing lots of these. And let's get extra practice and do another practice problem. And it's going to involve this basic conditions, right? So this reaction that occurs in basic solution can be balanced as if it occurred in acid, and then at the end, neutralize the H pluses by adding OH minuses to both sides. Just be careful that if you make water now and have it on both sides, that you're canceling out that water from each side like I've just shown you how to do. Okay, water should only appear on one side of the equation. So feel free to pause the video here, take as much time as you need to try to balance this redox reaction in basic solution. Identify reduction and oxidation, break the reaction into two, balance the elements and the electrons in each of those half reactions, figure out a common multiple to ensure that the electrons are going to cancel out, add the two half reactions back together, and then turn your H pluses into OH minuses and cancel out any waters. Okay, so feel free to try that now and pause the video before I solve it. Okay, so let's quickly go through and assign oxidation numbers just for practice here. We're actually told nitrogen has a charge of -3, which is helpful. Oxygen -2. And so then we can go through and see that carbon is going to be +2 because this molecule is -1 overall. Manganese here is going to be +7, just like the example we just did. Carbon here is going to be +4. +4 -3 -2 is -1 overall, so that checks out. And the Mn over here on the right is going to be +4. Okay, so manganese again is being reduced, so that's going to be one of my half reactions. This going to this. And my other half reaction here is going to be, maybe I'll balance this one first, Cn-, the oxidation, going to CnO-. And you can see I'm leaving some extra spots here on my paper because I know I'm going to be adding things to both sides likely. So I'm starting with it just sort of spread out. Okay, so here's the first half reaction. Let's go through and balance this. Okay, let's balance the not oxygens and hydrogens first. So carbons and nitrogens, well, one carbon on each side. So that's balanced. One nitrogen on each side, so that's balanced. The oxygens, I have one oxygen on the right, so I'm going to need an oxygen here on the left. Of course, I don't add just O, I add it in the form of H2O. And now my oxygens are balanced. Of course, now I have created an imbalance in hydrogens, and I'm going to need two hydrogens over here now on the right. Of course, I'm adding hydrogen in the form of H+, and so there's now two H pluses on the right. Now I can balance my electrons. Overall on the left, it is 1-. Overall on the right, it is 1- plus 2 pluses, so that's 1+ overall. And so now I pick the bigger of these numbers, 1+, and I'm going to add electrons to that side. How many electrons? Well, 2. And if it's not obvious, sometimes it isn't, just count down from the bigger number. 1. -1 is 0. -1 is -1. Okay, so that was 2. 1 to 0 to -1. All right, so I need to add 2 negatives to bring this 1 positive down to 1-. And now the charges balance. Okay, so this is now my first balanced half reaction. Let's go through now and balance the reduction half reaction. MnO4-, going to MnO2 solid. Okay, again, leaving lots of space here because I know I might need coefficients here and I know I might be adding stuff here. Okay, let's balance the manganese first. Done, 1 on each side. Let's balance the oxygen next. 4 on the left, 2 on the right. So I better add 2 waters to the right. Oxygen's balanced. Hydrogens now, well, I've introduced hydrogens now, so I better come back over here and add 4 H pluses to the left. Now my hydrogens are balanced, 4 on each side. And now I can worry about charge. Total on the right side is 0, everything's neutral. Total on the left side, 1 minus and 4 plus is 3 plus overall. And so now 3 is greater than 0, so I'm going to add electrons here to the left side because it has a greater charge and electrons are negative, and going to bring the 3 down to 2, down to 1, down to 0. So that's a difference of 3. So I've added 3 electrons here, and now my total charge on the left is 0, and my charges are balanced. Okay, so now I am at the point where I have balanced all my atoms and my electrons, and I'm ready to add these two reactions back together to make a whole reaction. But before I do that, I need to ensure that the electrons are going to cancel out. And I need to find the common multiple here. So I need to multiply the top reaction by 3 because I'm going to make these electrons 6 in the end. And I'm going to multiply this second reaction by 2 to make this second reaction have 6 electrons. All right, so the common multiple between 3 and 2 is 6, so I need to multiply reactions appropriately so that each reaction here has 6 electrons. So I go through and multiply everything in the top reaction by 3, so there's now 3 CNs, 3 waters, 3 CNOs, 3 times 2, 6 hydrogens, or protons I should say, and 6 electrons. I'm going through and multiplying the second reaction by 2, so there's now 2 MnO4s, 2 times 4 is 8 hydrogens, 2 times 3 is 6 electrons, 2 MnO2s, and 2 times 2 is 4 waters. And now I can add the two reactions together because my 6 electrons will cancel. Three CNs plus 2 MnO4 minuses, and I should include my states here. And then notice also that I've canceled the electrons, but I also have the ability here to cancel some waters. These 3 waters on the left, when I add to 4 waters on the right, is effectively just going to leave a single water on the right. And likewise, 8 hydrogen pluses on the left and 6 hydrogen pluses on the right, when I add these together, those 6 are going to get completely canceled with 6 of the 8, or leaving 2 H pluses on the left. Okay, so here I've added the reactions back together. I have 3 CNs, 2 MnO4s, producing 3 CNOs and 2 MnO2s. And then I did some accounting to make sure that I have 1 water in the end. 3 of them cancel out. And I have 2 H pluses in the end. 6 of them have canceled out. The electrons have exactly canceled. So now this is my balanced redox reaction if it was acidic conditions. Now I have this final step to turn it into a basic condition. And so remember, now I'm going to go through and cancel out any hydrogens by adding that number of OH minuses to each side. In doing so, those OH minuses neutralize the H pluses and make 2 waters. And now I can cancel the 1 water on the right with one of these 2 waters. And so the finale here, the final balanced reaction is 3CN minus AQ plus 2 MnNO4 minus AQ plus a single H2O liquid generates 3 CNO minus aqueous plus 2 MnO2 solids plus 2 OH minuses. And that is the balanced redox reaction in basic conditions. 3 carbons on each side, 3 nitrogens on each side, 2 manganese on each side, 9 oxygens on each side, and 2 hydrogens on each side. Check, 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 check. Okay, so make sure you take the time to practice these. As I said, they can be difficult, cumbersome. You can make a lot of tiny mistakes. You only get better by putting pen to paper and practicing them. So do take the time to get good at these, and you want to be able to do them, expeditiously under a time crunch that you might face on an exam. So that'll do it for this lecture. Next time we're going to talk about voltaic cells and how we can use voltaic cells to do something great, like build a battery to power light bulbs, etc., etc. And then after that, we'll talk about standard reduction potentials and tie it back to thermochemistry with something called the Nernst equation. But that'll do it for this lecture. See you next time.